So what we'll do today is we'll look at a little bit about diode characteristics, and then we'll look at the data sheets on the diode. This is not covered real well in your textbook, so the data sheet is the main thing, right? You understand? So these devices have part numbers on them, and if you don't have, if you can't see real close, and read real small things, then you need to go buy you a magnifying glass somewhere, because these part numbers are very small. So normally if we can get the part number off the thing, we can go to the internet and type in the number, and it'll give us a data sheet which tells us everything we need to know about the that's his type. This says chapter 3. I need to come back and do it. Like I said, the book has changed. I'm just gonna get this off here. And the figure numbers have changed, so I need a lot of work. This is what we refer to as a characteristic curve for a standard diode. Huh? Thank you. It's being recorded. So as it soon comes up, this is what we call a VI characteristic curve. And come on. And so what we have is so here's current. IF would mean when it's forward bias. IR would mean when it's reverse bias. And of course, this is voltage applied to the device. And so VF would be the voltage we apply to it to forward bias it, right? And VR would be the voltage we apply to it on reverse bias. Everybody okay? So what happens when we forward bias it? It is a semiconductor. A semiconductor will always conduct current. You'll understand that, because there is a path. So as soon as we, this is 0 volts, as soon as we apply a forward bias voltage, the diode starts conducting a little bit of current. That's so small we won't be able to measure it with the meters that we use. Okay. Now when this thing gets up around the forward bias, or what we call the VF, the diode starts to conduct. So first of all, it goes into a little knee. And then what happens, if we try to increase the voltage, the current just takes off. So it acts like a closed switch. But it always drops the voltage. The amount of voltage it drops, we use 7/10. We use 7/10 as an approximation. But it's a semiconductor. It's got stuff in there. So that means the more current you put through it, it drops a little more voltage. The less current you put through it, it drops a little less voltage. So this slope right here is not straight up. Y'all understand that? So we never say it is a closed switch. We say it acts like a closed switch. But it does drop a voltage. Everybody okay? Now we start reverse biasing that thing. This would be leakage current. And what controls the leakage current is temperature. So the hotter the temperature is, the more leakage current we get. The cooler it is, the less leakage current. But we keep increasing this voltage, and sooner or later this sucker is going, we call it avalanche or breakover voltage, and this is not good. So a standard diode, if you exceed this and you don't protect that thing, then it's going to bop it just like that. Now what happens with semiconductors when they go bad? Well, a resistor, when it goes bad, its resistance goes up. I've never seen a resistor short, but I've seen a shorted resistor. Y'all understand the difference? Because things happen. People drop things on the circuit, or they don't solder right, and they do different things. Solid state devices can either open, or they can short, or they can become leaky, which is it's not good either way. So that means they would conduct a lot of current in the reverse direction. But anyway, we lose characteristic of the thing. So when you break it over in the reverse direction, then it's hard to say what the thing's going to do. Of course, if it shorts, you got a big problem, right? You understand that. If it becomes leaky, you probably got a fairly big problem because things are going to be getting the wrong polarity. Instead of get DC, it's going to get a little bit of negative AC or the other. Huh? It's not in a chapter. It should be under diodes. I don't know. Yeah. Yeah, I was going to say, the problem is we've changed books a couple times in this thing, and I don't remember to go back and change the power. Now, the problem is, for me to actually know this voltage drop, what would I have to know? Well, I'd have to know the current flow through the device. I would have to know the resistance of the device at that current flow to calculate the forward voltage drop. So this drop, we call it the VF, right? And this is the voltage drop across the diode when it starts conducting, when it's forward biased. We call this the breakover voltage. And some people call it the avalanche voltage because it's what it looks like, right? Data sheets, this is going to cause it, they call it the breakover voltage. This is bad. So we never want to exceed this on purpose. So that's one of the things we do when we choose a diode. One of the things in the specification is the breakover voltage. And you want to make sure, and that's a voltage. So, you know, when we deal with RMS, we don't understand peak, but this is a voltage. It's not an average voltage. So, you know, if you've got 120 volts RMS, 120 volts, and you use a diode that's got a breakover 120 volts, you're going to bop that thing because it's got almost 170 volts peak, right? You understand that? So that's one reason you need to be able to figure peak voltage. So what we do though is trying to figure out this. I would need to be an engineer, but we're not engineers in here. So what we're going to do is just like our resistors. We got two things. When I look at the color code of a resistor, is that the resistance of the resistor? No, it's got a tolerance. But I could sit all day out there, if I'm an engineer, I could sit there with my ohm meter and measure, and use the measured value, but now I'm wasting a ton of time, right? You understand? When everything else has a tolerance. So what we do when we engineer a thing, we use the color-coded value. Y'all understand that? We don't use the calculated value, we use the color-coded value. But we understand now that if I use the color-coded values, my math is going to be perfect, but my measurements are not, but they're going to be real close, right? You understand? So we'll know by our calculations when we compare so if I calculate 7 volts and I measure 3 volts, I got a problem, right? You understand? If I calculate 7 volts and I got 6.4, then we don't have a problem. Or if I've got, you know, what did I say? If I got 8 volts, we probably don't have a problem, right? You understand what we're saying? So all we do is we use approximations. So this is forward bias. So what we do, that's reverse bias. We've already looked at the symbol. Everybody okay here? Okay, this is the symbol for a diode. It's supposed to be colored in, but you're going to see me up here a lot. I don't color it in. A lot of people don't because it just takes time. The arrowhead itself is representing the P material. And then the bar right here represents the N. And that's basically what it tells you what you have to do to forward bias. So does that mean we need to make the cathode negative and the anode positive? No. It just means the cathode has to be more negative, less positive than the anode, right? Or the anode's got to be less negative than the cathode. So odds are if you ever see a negative on the cathode and a positive on the anode, there's a good chance that the diode itself is bad. Y'all understand what I'm saying? Yes or no? Huh? A good example. So normally in a circuit, we establish common, right? So if I was to come up here and look at this circuit right here, and we'll put a battery right there, or a DC voltage source. And then I'm going to forward bias my diode. So I'm going to turn the anode toward the positive, the cathode toward the negative, right? You understand that? And then we'll come over here and we'll put a resistor. And then what we're going to do is we're going to establish this right here as our circuit common. So that means I'm going to make my measurements, when I make my measurements with my voltmeter, I'm going to put my black lead on the common. And then I'm going to come over here and I'm going to measure right there. Well, let's say this was plus 12 volts. Well, all I'm doing is measuring across the source. Y'all understand this symbol? We have a problem with people with this symbol right here. That symbol represents something. What does it represent? It represents common, but it also represents a wire. Y'all understand that? So usually in DC, you come up here, you'll start drawing these circuits like this, right? You know, y'all understand. Y'all come over here and you'll put this, and then you draw that wire. What people don't understand is that the more wires we put in a schematic, the more cumbersome the wire gets, where everything is hooked to a common. They might have a different source, but everything would be hooked to a common. So instead of drawing the wire that represents the common and drawing everything connected to it, we use a symbol to represent a wire. But the wire has to be there. So this happens a lot in this class where they'll say, well, I thought that was in the trainer. It's common. I thought the wire was in the trainer. Well, it's not. It's a wire you have to hook up that we're representing with a symbol, right? You understand. But it usually means we make all our measurements relative to common. We try to prevent putting a voltmeter inside a circle, because then you're across, right? You understand. So normally what we do is when you see all these calculations, they're going to be relative to common. So that way you can get an alligator clip. Most meters come with a nice alligator clip, and find a good common, clip onto it, and then you're probing with how many leads? You're probing with one lead, which makes it extremely less dangerous. So I needed to bring that up because almost every time I teach this class, people see that symbol and they think that's a common, and they don't understand the common is representing a wire. So what would I measure right here? Well, I'm measuring across the source. I'm measuring across the source. So what would it measure? It would measure 12 volts, right? You understand? Okay. Well, what's it going to measure when I come over here and take that red lead and put it right here? It's going to measure a positive 11.3 volts, because the diode drops 0.7 volts. I mean, it would measure half if this was it don't make any difference the size of this resistor. If that was a 1K and I had another 1K, that would drop, but the diode drops 0.7 of a volt. Supposedly, we know right now that it don't drop at 0.7 of a volt. It starts conducting around 0.5. Then it varies with current. But for me to know the exact voltage, I would have to know a lot of stuff about the diode. But look, by George, they're both positive. Well, Rich, you said the cathode had to be negative. No, Rich never said the cathode had to be negative. We said it had to be 0.7 of a volt less positive. So that means if I put my common right here, right, you understand, and measure there, it would measure minus 0.7. But normally we don't make measurements across. We try to make it relative to common. And we could do the same thing. I could flip it around and use the negative supply, turn my diode around, and both sides would be what? Yeah, so you're right. I could come over here and I'm going to come over here and so if you ever see on a test, and you're going to see this on a test, the cathode has to be negative and the anode has to be positive, you're going to mark that false. Because odds are you're probably never going to see that. Okay, guys, what would happen now? Let's say this is a silicon diode. So what would I measure across my resistor now? The problem we have is the 7/10 of a volt, number one, only comes into play when it's forward biased. It don't come into play when it's reverse biased. It comes into play when it's forward biased. Normal tendency, people look at silicon and they say 7/10 of a volt. And another thing they don't look at in this class is they don't even look to see if the dang thing's forward biased or if it's reverse biased. So here we have the anode pointing, we have this P pointing toward an N, and we have the N pointing toward a P. So this guy here is reverse biased. When it's reverse biased, it acts like an open switch. An open switch does not let any current flow. To get voltage drop across my resistor, V is equal to I times R. So let's say this is a 1K. So V across my 1K is equal to I, which is 0 times 1K. So V across my resistor is going to equal 0 volts. And with our meters, that's what we'll see. If that was a 10 mega ohm resistor, we might see 600 millivolts because there is leakage current going through there. Understand that, but it's so dang small, our standard resistors we won't see. 10 mega ohm is practically an open circuit, right? You understand that. But there is current flow through there. So we'd measure about 0 volts. What would I measure across the diode? This is a 12 volt supply. It's an open, yeah. Huh? What would it measure? Yeah, it's going to measure 12 volts. Why is it measuring 12 volts? Well, the resistor's dropping none. So if it's dropping none, it's acting like a piece of wire. And people think resistors drop voltage. Resistors don't drop voltage unless they have a current flow through them. Y'all understand that? So if it drops no voltage, that's effectively putting that thing right there. Kirchhoff's voltage law says all the voltage in a circuit has, and people wonders why an open in a series loop drops the applied voltage because there's no current flow anywhere in the circuit. So I could go over on that light switch over there and I turn it off, I measure across it, it's going to measure 120 volts because these lights are not dropping any voltage, right? Because they don't have any current flow through them. So if I go over and I say, what should I measure across the switch? We got 120 volts applied to a circuit. What should you measure across a closed switch? Very important to know, guys. This will get you killed. What should you measure across a closed switch if I've got 120 volts applied to it? What should be measured? What should you measure? How much resistance does a closed switch have? Huh? None. Okay, so V is equal to I times R. So V is equal to 100 amps times 0. What's 100 amps times 0? 0. A closed switch should drop nothing. Y'all understand that? And people will do that. They'll go over there, well, let's see if there's power on the switch. And they measure across the switch. And it measures 0. Oh, there's no power on this switch. And they stick their hand in there, and they're working in industry, and everything's metal, and everything's grounded. It might not hurt you much here because, in residential, we use mostly plastic boxes. But in commercial and industrial, we use metal boxes, and those metal boxes are grounded. So that means you get your hand in that metal box, right, you understand. It might not kill you, but it sure burn your hand, man. So remember, when you measure across a switch, if the switch is closed, you get 0 volts, right? You should get 0 volts. And that's true of a circuit breaker, too, by the way. So that's the way you can check a circuit breaker. So let's flip the diode around. We're going to keep the same common. How many people are going to miss that on the test? You're going to see silicone, You're not even going to look at the diode to see if it's forward bias or reverse bias. You're going to say it's going to measure 0.7 of a volt or 11.3 volts. And of course, you're going to miss that. Last time I taught this class, I put that same dang question on all 4 tests, and we had people miss it on all 4 tests. What can you do? So now we got it forward biased. So what would my meter read? I'm going to get rid of this meter right here. Got a silicon diode, so we're going to use approximately 0.7 of a volt. And the first place we're going to do is we're going to take our red lead. Our red lead. So your red lead is not your positive lead, it's your measuring lead. Your black lead is your common lead. So a meter common does not have to be circuit common, right? You understand that. You can put a meter anywhere you want to. So your voltage measurements are relative to your black lead. So in AC, where do you need to put your black lead at? Don't make any difference. AC has no polarity. You get people talk about that too. You're going to put that black lead on the neutral. In AC, you don't. In DC, you don't. But DC, if you put it on there backwards, your voltage measure, your polarities are going to be backwards. Y'all understand that? But digital meters don't care. Analog meters you could mess the meter up on DC if you put it in backwards, because it's got a pointer on it, and if you put it in backwards and it swings over and pegs against the stop, you could bend your pointer. So what would I measure if I put my red lead right there? Still 12 volts. What do I get, guys? Yeah, we could say 12 volts, but technically that's incorrect. It's going to measure a minus 12 volts. Yeah, because our red lead is on the more negative potential, right? Okay. So what would I get if I came over here and moved my red lead over to the other side of the diode? It's going to measure a negative 11.3. Because it's going to drop 0.7 of a volt. The anode's got to be more positive than cathode. So the anode, if I go more negative, then the thing would be reverse bias. This guy is pointing toward the positive side. So if it's pointing toward the positive side, this side has got to be less negative. Okay, y'all understand that? But notice here, both sides of the diode measure negative. But look, the anode is 0.7 of a volt less negative. So if it's 0.7 more volts less negative, then it's positive in respect to the cathode. Y'all understand that? So what I'm trying to get at is that, people teach that the anode's got to be positive and the cathode's got to be negative. They don't understand the diode, and it's going to get you in a lot of trouble. Because odds are you'll never see that. If the cathode is connected to common, it's going to measure 0 volts anyway. Well, here's forward bias. Here the cathode is pointing toward the negative. So what you need to do is if you label this an N and you label that P, it means to forward bias it. The cathode has to be pointing toward. It don't have to be connected to. It's got to be pointing toward the negative potential. And the anode has got to be pointing toward the positive potential. Huh? Yeah, on diodes, the electrons flow against the arrow. And I told y'all the history on that, right? About when they first made the symbols, they were using positive flow. Because originally when they came out with electricity, they knew that charged particles were flowing. They knew that. So when they assigned these polarities, they went according to from high pressure to low pressure. And what they assumed at the time was positive was the high pressure and negative was the low pressure. But that's not true. It's just like when we have high pressure, low pressure systems. Each one of them's a pressure, right? You understand? And what do pressure systems do? Well, they cause the wind to flow. One of them flows around it clockwise, the other one flows around it counterclockwise. But basically, it's still pressure. But we call it low pressure because it's so below so many millibars. But it don't. All it does is change the direction of the wind flow. We still have wind flow. And when you have high, low pressures and low pressures that come together, real low pressures and real high pressures come together, that's when we get problems. So the winds, so one's going this way, y'all understand that? So one's going this way, one's going this way, right? And what do? They combine right there, and that's when we start having bad stuff. High pressures and low pressure. So make sure you look at if first of all, you're going to determine if it's forward bias or reverse bias, right? Y'all understand that? When it's forward bias is when you're concerned with what type of diode it is. When it's reverse bias, it makes no difference. Because when it's reverse bias and it's in a series circuit, it's going to drop the applied voltage. Of course, there wouldn't be much use for this. We have them on our chargers. So on your circuit, inside your phone, you have a diode. Y'all understand that? And the diode is pointing toward the charger. And then this comes into your charging circuit, and then your batteries are in here. And then you have a common. Well, you hook this up to a DC power supply, and people do stupid things. You know, their phone don't charge and their cord breaks, and they go out and get another charger, and they cut the wire. It's all USB, and they twist them together. They get the positive and negative reversed on their patch cord. And if they plug it in their phone, if you put it in backwards, it'll burn up your phone. But if they put it in backwards, it's not going to hurt anything because that diode is protecting the battery, right? You'll understand that in your charging circuit. So if I came up here for some reason and I put a negative right there when it's supposed to be a positive, it's not going to hurt your phone at all, right? So most chargers, most computers. So this guy right here's got a diode in there. So if my cord breaks or this one goes out and I go out and find another one that fits in there and I go in here and I cram it in there and it's got an opposite polarity to my other charger, then it's not going to hurt it's not going to hurt anything. Why? Because they've got that diode in there. So we run into this little thing all the time that protects charging circuits, especially if I have a removable charger, right? You understand, a removable charger. Of course, none of y'all would do anything like that, right? Yeah, that's the problem with some electronics people. You know, they say, well, I do that all the time. I mean, I don't put them in there backwards, but, you know, I'll have a cord break and I say, well, I need a 15-volt charger. I've got boxes of these chargers. I know it needs 15 volts. I clip them off. I'll twist the wires together and I'll do that. But I understand what's going on, right? Double checking polarity and stuff like that. But people do that. They do that in AC too, and they'll twist the neutral in the hots and get somebody killed. It's just two wires. So normally what we do is, of course we've already looked at these. These guys come in all shapes and sizes, right? What we do is we use, so just like when we use the color-coded value, y'all understand that's what we call an approximation. Y'all understand that? So if I see brown, black, red, what resistor would that be? By the way, in my classes, if you come up there and say, Rich, I need a 1K resistor, I'm going to say, what's the color code? Y'all understand that? Now, I know the color code. But this is something you need to start learning, right? It's trying to use a little chart and trying to use that little memory thing that we come up with. If you depend on that all the time, it's going to get you in trouble. I really learned the color code when I went to work for U.S. Steel, of course, I was a newbie, and they had a drawer full of resistors. And they said, Rich, we want you to sort these into individual drawers. And I realized real fast I needed to learn to color code. So it didn't take me long. I was chucking in things, just looking at them so I have no problem with color code. So we're gonna make that requirement too. So I'm gonna tell y'all, be prepared for that. So we have what we call first approximation. We usually deal with this, if I'm dealing with a diode that's connected to 100, 200, 250 volts, taking out the 7/10 of a volt is a waste of time. Right? You understand that? So normally, the higher the voltage, we're going to deal with what we call first approximation. First approximation is you teach the diode like it's ideal. So you teach it when it's forward bias. If it's forward bias, you say it drops 0 volts. If it's reverse bias, you say it drops all volts. So this usually takes place around 50 volts. Usually above 50 volts, we'll use first approximation. Below 50 volts, we'll use what we call second approximation. So what we're going to do is we're going to use second approximation, which they call, which basically is what we've already been using. So second approximation is this. If it's silicon diode, we say, okay, it's going to start conducting at what? 700 millivolts, and this line goes straight up. And then when I reverse bias it, it blocks everything. This is second approximation, and this is what we're going to use. Is it perfectly accurate? No. Is it close enough so I can tell if something's working or not working? Yes. Plenty close enough. In fact, we used it the other day, right? We used the rated voltage on the transformer that said 110 volts to get 12.6 volts out. And we calculated 5.6 volts, and we measured 6.4, I think. So I think it was like 100 millivolts difference or something like that. And we realized that when we looked at the transformer, it was actually getting over 120 volts instead of 110, what it was rated at, right? You understand that? But even though I used all the values that was marked on the thing, it still worked. And we used 7/10 of a volt, and it still worked out good. Third approximation, which we won't use, you use this if you're an engineer and you really, really, really want to calculate this out. That's when you have to know all these characteristics about the diode. So you need to know the leakage current, you need to know the knee current, you need to know this angle right here, and that's what would be used in third approximation. So are we going to use this? No. If you're an engineer, you might use it. Odds are you wouldn't even use it then. But it's available. So first approximation, we teach it like we would treat it like it's an ideal diode, right? You understand that? Usually we do this when it gets around 50 volts. We're not going to deal with anything that high, because anything above 50 volts is considered to be a lethal voltage. We don't deal with lethal voltages in this class. And PPE is not required. Any PPE is not required under 50 volts. Talking to my troubleshooting class. So y'all know what y'all did, right? You said always required no matter the voltage. That's not true. I see all these auto mechanics out there with all this PPE on. No, so it's not always required. Just above 50 volts, so we got to start looking at personal protection equipment. Above 50 volts, below 50 volts, PPE is not required. Y'all understand that? Like now we do. Okay, so everybody okay on how to check these things? Check it with an ohm meter. And we explained how an ohm meter actually works. We still say check it with an ohm meter. But what it does when you flip it over to the diodes, we call this the diode scale, but this is what we call the p-n junction scale. That's technically what it is. So any device that's got a p-n junction, we can use this meter to check. So we call it the diode scale, but technically it's a p-n junction scale. Normally the diode scale has two functions. It's a continuity checker. What's continuity? You need to know terms, guys. What's continuity? Well, you can't say continuous. You understand that? Well, it's because I could have a piece of nichrome wire. Nichrome wire is used inside of heaters, and that would be a continuous strip, right? You understand? So it is a resistance between 2 points that has little or no resistance. We call that continuity. So I'm going to put that on one of the multiple choice there. You better be careful. So it's not a continuous path. All circuits are a continuous path, right? You understand that? So all closed circuits are continuous path. So if we put it on the diode scale, what's going to happen? Now the polarity of the meter becomes very important. You need to make sure you have your black lead in the common. You need to make sure you have the red lead in the one that's got V on it, or ohms. That's a shared scale. Okay. Put it on here, and then if the silicon is going to measure about 700 millivolts. Most of your newer meters actually measure millivolts, by the way. And then if it's reverse biased, it's going to show something quite a bit larger. Some meters show open. Most of your new meters show overload. Overload means it's an open. But like my Sperry, don't do that. So the first thing you need to do is just turn it on the diode scale and put your meter leads up in the air. Don't let them touch anything. And whatever it shows you, that's what it gives you when it sees an open. Y'all understand that? So if it says overload, that means when I reverse bias a diode, it should come up and give me OL. If it shows another voltage measurement, that's what it'll get when it's reverse bias. But the ratio is going to be extremely high, right? You understand that? Are we okay? And we showed y'all that you could check it with an ohm meter too sometimes, but we're looking for on an ohm meter, on a true ohm meter, we're looking for a real high forward to reverse resistance, right? Ratio. So here they're showing a bad reading. So here we have it what? We have the black lead on the cathode. By the way, cathode is abbreviated with a K. Y'all understand why? Because C is already used for capacitors. So here the cathode, now the anode, they're doing A, but K for cathode. We have a black lead on the cathode. We have a red lead on the anode. This should be forward bias. This should either show around 0.7 or around 0.3, right? 0.7 would indicate it's a silicon diode. Around 0.3 would indicate it's germanium. So here they're showing us the same thing they were showing us over here when it was reverse bias, right? You understand? So this is what it's showing us when it's open. Over here it means this diode right here is open. Now over here it's measuring 0 volts when it's forward biased. It should be measuring either 7/10 or 3/10, around that. So it means this diode is shorted. Everybody okay? What if you measured the same thing in both directions, forward and reverse? It means the diode is leaky, which means it's still bad, right? You understand? So that's something you need to understand, because there's diodes that are bad. So you should get around, now I'm not saying around 7/10 of a volt, forward biased if it's, what type? Silicon, right? Around 3/10 when it's germanium. And when you flip it around reverse bias, it should measure an open. So if you measure something different in both directions, you know, if you don't measure around 7/10, if it measures around 8 or 9, then you know you got a problem, right? Yeah, especially with LEDs. A lot of times we can. Let's say I wanted to work with 1,000 volts. Well, there's no diode out there that can block 1,000 volts. But if I can find 2 diodes that have 500 volt ratings, then you put them in series, and then the breakover voltage rating of the diodes add together. So an LED is a good example. Light emitting diodes are great, but they have real low breakover voltage. So if you put an LED into a 120 volt circuit, it's going to pop it every time, even if you put it, no matter what resistance. But you could take a regular LED and put it in series with a diode that's got 200 volt breakover, and the LED would work right. So yeah, we use them in series all the time. The number 4 galvanizing line at US Steel had DC cranes, and they used diodes to get the 250 volts. And you went into those diodes, and they were just hundreds of diodes in series with each other. And that why? Well, not to drop the voltage, to prevent them from breaking over. Okay, to prevent them from breaking over. And you only lose 7/10. If it's silicon, you only lose 7/10 of a volt per diode. I mean, so you got 300 volts or all this voltage to work with, you know, and you got 7 of them in series, then you're only going to lose 2.1 volts. So what's 2.1 volts, you know, on 500 volts? It's really nothing. So yeah, you'll see them in series. It's not for the current though. Usually when we put them in series, it's for the breakover voltage. So good question. Any more? This is a power supply that we'll get in later on. This is what we're into right now. And so this guy here has 4 diodes in it. And we'll come back to this once we look at it. So we'll try to figure out. So this is the guy going in here, or the lady going in here making measurements. And hopefully from this later on, we'll be able to figure out what's going on. By the way, ohm meter in the circuit. What should be the power when you put an ohm meter in the circuit? Should be off. Everybody understand that? So we got 2 meters we measure across with. And that's our ohm meter, and that's our voltmeter. Voltmeter, we make our measurements usually with power on, unless we check it to see if power's off. And by the way, that's something you should get in a habit with. Just because you flip a breaker or just because you do something does not mean that the circuit is wired the way it's supposed to wire. So when you trip a breaker or pull a disconnect, you always check where you're working for power, for voltage, right? You understand that? That should be something you get used to doing right off the bat. So before you put an ohm meter in a circuit, first thing you should do is put it on volts and check to see if there's a voltage there. Because you could damage your meter. It could damage you too if the meter blows up. Just a few little safety procedures. Don't make any difference how many years of experience you got, right? Okay. So everybody okay on the approximation? So what approximations are we going to use? We're going to use second approximation. What's second approximation? That means for silicon, we're going to use what? 0.7 when it's forward biased. For germanium, we're going to use what? 0.3. That's not what it's going to be, but that's close enough. When it's reverse bias, 7/10, and don't come into play. But I guarantee you, this class is small. We only got 7 people on here. That question is going to be on a test. The diode is going to be reverse biased. I'm going to say how much voltage drop across the resistor, and it's going to be 12, and somebody's going to put 11.3. Somebody in this class is going to do that. But all I have to do is just put that little SI up there, saying it's silicon, and for some reason that 7/10 of a volt drops in your mind, and you don't even look to see if it's what? Forward or reverse bias. Huh? No, because it's an open switch. I mean, it drops when you got an open diode, it drops the applied voltage. Not an open diode, when you got a reverse bias diode. And if you're looking at and what we were getting into, of course, was our power supplies. So what we're doing is we're looking at the top of the formula sheet, the second group, which deals with rectifier circuit. So in your textbook, the textbook probably does a little better. So the basic makeup of a power supply. So first of all, we're going to talk about what we call unregulated, unfiltered supplies. This is chapter, I need to make the chapters right. In the textbook, this is chapter 6. Chapter 6 says DC power supplies, operation and troubleshooting, right? So, okay. Talk about the DC power supplies, half wave rectifiers, full wave rectifiers, center tap full wave, and full wave bridge rectifiers. Now, what advantage does DC have over AC? Huh? That's not the advantage. We can control it electronically. So transistors work off of DC. Everything that's electronic works off of DC. What advantage does AC have over DC? 2. Can't say it's cheaper. I'll pay for watts. Right? So 100 watts DC and 100 watts AC would cost me exactly the same amount of money. We don't pay for DC. We don't pay for AC. We pay for watts. But when they transmit the power, they transmit it in AC over here. Now we'll talk about, in AC, we'll talk about the problems with transmitting power AC, but it has so much more advantages over DC. Trying to transmit. What advantage, and I just gave y'all the answer. So what advantage does AC over DC? Is that we have the ability to transmission, getting it from point A to point B. Trying to get it from a station. You know where we get the power here at the college? You know where it comes from? It comes from TVA. It's the Tennessee Valley. We come from the Tennessee River. The plant. How in the world can they get all this power from Bessemer down from the Tennessee River? Huh? Well, the trick is that we're trying to transmit power, right? Now, what determines the amount of power? What's our main power formula? Power is equal to what? We got 3. Yeah, E times I or V times I. Okay, don't understand that. Okay. So what determines the amount of current? Well, I is equal to P over V. What determines what determines the amount of voltage drop we get across something? V is equal to I times R. So every wire has a resistance. Every wire has a resistance. And think about the wires running from the Tennessee River down to Bessemer, Alabama. You know, if they had 1 ohm, and think about this, if you had 1 ohm of resistance in your starter leads, the wire would drop more voltage, and no matter how good your battery was, that's one of the first things you check if your car don't crank. You check the connections. Because if you got 1 ohm, 12 amps would drop 12 volts, right? You understand? And if you drop 12 volts in your conductor, how much is left over for your starter? None. So if your car don't crank, you don't go out there and change your batteries. One of the first things you do is what? Check the connection. Then you check the water, of course. So that means, okay, if my wire has resistance, and I want to make it drop a smaller voltage, then what I want it to drop less, and now the wire gauge has nothing to do with voltage. What does a wire do? what does a conductor do? The actual conductor. What's his function in life? Conducts what? Current. Conducts current, right? You'll understand that. So the wire gauge determines how much current it conducts. Not how much voltage you apply to it, how much current it conducts. The insulator determines how much voltage you can apply to it, because the higher the voltage, it's looking for ground, right? It's looking for the other conductor. So we put insulators on them to keep them from trying to conduct through air, right? You understand that? Or when they come in contact with each other. And plus now, if it's got an insulator on it, then I can touch the conductor, right? You understand that? Has nothing to do with that. So if I got two options, and what determines the amount of resistance the wire has? We call it the gauge, which would be the size. What else? Yeah, well, let's go. The material. We have two primary materials used as conductors. We have copper and aluminum. Okay, then what else? Well, let's go. Temperatures last, then the length, and then the temperature. The bigger the wire gauge, the more it's going to cost. If I go from copper to aluminum, aluminum has more resistance, the more it's going to cost. Right? Copper is very expensive. Aluminum, relative to cost, aluminum is quite a bit cheaper.
Did you say copper has more resistance?
I didn't. If I said that, I didn't. Aluminum has more resistance.
I didn't think you meant to, but I'm like, maybe I heard it.
So that means if I can come over here and pump, so let's say I want to send 1,000 watts, and I do this at 100 volts. How much? What would the current be? It would equal to 10 amps. Let's say I'm sending 1,000 watts, and I'm doing it at 1,000 volts. 1 amp. So that means the higher we make the voltage, the lower the current. The lower the current, the less line loss we have in the lines. So if I can step it up, but I'm not trying to sell you your current, I'm not trying to sell you voltage, I'm selling you power. Right? You understand that? So what I can do is I can step the voltage up extremely high for transmission. So that means if I use 750,000 volts, I could send 750,000 watts of power with 1 amp. You'll understand that. But I can't get around 750,000 volts. It'd be like Eagle Eye. Y'all remember Eagle Eye? Y'all see that movie? Where that big high tension line fell on that guy? And what happened to him? He just evaporated. And it would do that too, believe that or not. So we step it up extremely high for transmission, and then we step, what advantage does low voltage have over high voltage? Just safer. Yeah. So we step it down for use. So we have devices called transformers, and that's their functional life. They don't change the power. They do a little bit because there's no such thing as a 100% efficient transformer. But most of the transformers now are well over 95% efficient, which means, you know, if I get 100 watts out, it'll put 100 watts in. We might put 105 watts in to get 100 watts out. So for practical purpose and for approximation, we'll say that they're 100% efficient. So what we'll do is we'll step it down, we'll step it up for what? Transmission. And then the closer we start getting to us, we start stepping it down until we get it to our house. And we have two houses, we have two voltages available in our house. We call 240 and 120. We run our high wattage loads on 240, and we hide those plugs, or we direct wire them, right, because it's very dangerous. And then all our plugs are what we call 120, because it's safer. Y'all understand that? So this is the guy right here. So the higher I can make the voltage to send that power, the less current it requires. So now instead of using copper, I can use aluminum. Right? To get it from point A to point B. Then we get it into our house, and I got a TV that don't run off AC, it runs off of DC. So we have what we call a power supply. Now the function of the power supply is to do what? Take AC and give us the required DC. That's the function of power supply. So what's this? So on this side I have Alabama Power. On this side I got DC. There's my power supply right there. So inside your TV is a power supply. Inside your microwave is a power supply. Inside your radio is a power supply. Y'all understand that? So if we don't generate AC, your car generates DC, so we're okay, right? You understand? But we don't transmit that over great distances. By the way, with what we have available in solid state, they are doing some, it's not for use, but they're doing some extremely high DC transmission now. They don't step it up with a transformer, they step it up electronic, which is pretty neat. And we don't have time. And AC, we'll probably discuss that because of the other things that come into play with AC that DC don't have a problem. So the function of a DC power supply is to do what? This is the most common circuit in electronics. It should make sense. So everything that's electronic has a power supply in it, right? You understand that? Even if it regenerates AC. So your car radio regenerates AC. We can't put DC into a speaker. It'll burn the speaker up. So your car stereo generates AC. But to generate the AC, it starts with what? DC. DC is used to power almost all electronic devices. Rectifiers. This is the circuit. This is the name of the circuit components that converts DC to AC to DC. So inside your alternator, you got a rectifier. It's just a bunch of diodes. That's all it is. Later on, we're going to learn about. So what we're going to do is we're going to start off with the power supply. Let's see if I got them here. So this is the power supply we're going to start off with, and this is the one we looked at the other class. And so I had a transformer. Where's my power supply? Oh, where's my power supply? Well, I had the other day. Oh well. Oh, here it is. It fell off. Nothing. Then we're going to end up here. We're going to start off here with nothing but diodes. That's not true. We could do this, but we're not going to do that because we'd be dealing with pretty high voltage over here. So ours is going to look like this. We're going to have the plug. Then we're going to have a transformer. What's the function of the transformer? Yeah, it's whatever we need, whatever do. So we could step up or we could step down. A lot of people say steps down, but that's not true. Could step up. Then we're going to run into the rectifier. And the rectifier, then later on we're going to add the filter. And then later on we're going to add the regulator. Okay. Huh? Yeah, that's what I was just okay guys, let's take a break. Thank you, Larry. It is break time. That's what I was referred to as a half-wave rectifier. And this is the one we looked at the last class. So these guys are very simple to make. So my schematic I have up here connected is I have a step-down transformer. Here's my calculator. Just saying. Oh, yeah, I froze the screen because I was,
Okay.
so I was, showing some stuff y'all were supposed to see. We're using a transformer that's got an 8.7 to 1 ratio. And the transformer itself is center tap, but what we're going to do is we're going to use it just like it's a regular transformer. We talked a little bit about center tap transformer last class, right? And so what we're going to do is, when you run into transformers, what you need to do is be able to figure the ratios, because a lot of times they don't show the primary with more turns than the secondary. Usually the symbols they show are going to be the same size, so you need to understand the ratios. So this is what we got. We got center tap transformer. We're not using this lead. We have it disconnected. I have a diode pointing in this direction, and then I have a resistor. And then, of course, we should fill this in. But if you don't do it, I won't take off point. Normally, we don't draw the return wire. Why do we usually use a symbol that represents the return wire? This is a common. This is the symbol for a common. Y'all know the difference between the common and ground, right? And this is two of the most misused terms in electricity and electronics, common and a ground. Y'all know the difference between a common and a ground? Common don't either. You can't say, well, nothing carries voltage. Y'all understand? Voltage don't move. It's just the pressure. We have a pressure loss, but the voltage itself, that would be like the power supply moving through the circuit. We got one power supply. We got one heart. Your heart doesn't move through it. But we measure our blood pressure, right? Common is just a reference point of a circuit. Ground is a copper rod drove down into earth ground somewhere and a wire connected. Okay. It used to be copper, now it's usually copper plated. Because the only thing you need is what's on the outside. If you put it, and it don't carry current, so, you know, so it's pretty good size to get more surface area against the ground. But the inside is usually like aluminum now, and it's copper plated. In the old days, it was copper. If you ever find some of those things and dig them up, you probably worth a pretty good deal of money. But
Just out of my curiosity, is your diamond going first line?
it's AC. Now, this is a symbol of a transformer. It's going to be reverse bias one way and forward bias the other. Now, if that was a DC power supply, on AC, it's going to switch between the two, and that's what it is. That's what a check valve does, right? You understand? We put it on AC, so over here I've got current flow trying to flow in both directions, but it can't flow in one direction because we're blocking it. That's okay. So people call this ground all the time. This is the symbol for a ground. 3 dots, going smaller and smaller, not 4, not 2, 3 lines. This is a symbol for a ground. But you see it's misused all the time. And they'll call it ground. They'll say your bracket lead's supposed to be connected to ground, and it's not connected to ground, it's connected to the chassis of your car. So the chassis of your car is a common, right? This cell phone doesn't have a ground. It's got a common, right? You understand that? So you need to understand the two, even though it's a misused term, and calling it ground is not going to be a big deal, but you need to understand the difference between a common and a ground. So that's a common, because I lose my ground, even though this side of Alabama Power, when I plug this into Alabama Power, this side right here is connected to ground if I don't break off the center lead. But as soon as I come through that transformer, then ground's gone, because that energy is transferred magnetically. So if I wanted the secondary of a transformer to be grounded, I've got to ground it. Y'all understand that? So this is why you got a ground. So 8.7 to 1. So over here it's rated at 110 volts. So what should I expect across here, which is what we're using? So it means this guy here is going to divide we got for every 8.7 turns on the primary, we have 1 turn on the secondary. So this guy here is going to divide the voltage by 8.7. So if I put 110 volts in, what should I expect out? Huh? Yeah, y'all need to get your calculator out because you're going to be using them. Unless you can do math real good in your head real fast. So what should we spec out? What should we expect out? This transformer likes to hum or something. It should be humming, it's not. Is this so hard, guys? I can do this. So I'm going to take 110. I'm going to divide it by 8.7. I'm going to hit equals. And what do we have?
1.643.
Yeah, so this is this would be a 12.6 volt CT transformer. What does the CT stand for? So if y'all don't know what that means, y'all gonna have a problem. So I'm gonna come up here and look at this transformer right here. Don't give me the turns rate. Huh? CT. So here it is right here. 12.6 volt CT transformer. Can y'all see it right there? So what does the CT stand for? It's rated at 1 amp. Yeah, it's center tap. So if we go between the center tap and one of the legs, the other legs, then we'll get 6.3 volts, right? Which is very popular for the heater voltage on vacuum tubes. And that's why a lot of your transformers still have 6.3 volts because of. Okay. So that's going to be, but this is RMS, right? Y'all understand that, root mean squared. So the first thing I would do is I would take this, and we looked at this the other day. The first thing I would do is take that, regulators in the circuit. This is what we're looking at. First of all, we're going to start off with this. These are the first circuits we're going to hook up. Well, actually, we're going to start up with this. So we're going to have a watt. The first block is going to be a watt transformer, right? I'm going to run out of space. And then the second block, we have 2 wires, is going to be the rectifier. So this is, the book is more correct than we are. This is what we're going to work on first. Okay. Then later on, what we're going to get out of this is we're going to get this guy right here. We call this pulsating DC. So we'll look at this with an oscilloscope. What's the difference between an oscilloscope and a meter? Exactly right. What does a meter do? Yeah, it averages there. Yeah, it averages everything. So we're going to be let y'all play with an oscilloscope. I closed out my camera. Dang it, Rich. Let's play around with an oscilloscope in this class. A meter's great, but in electronics, oscilloscopes really show you what's there. Don't make much difference in DC because DC is DC, right? So your meter does a real good job on DC, but varying signals it doesn't do a good job. So there we go right there. That's actually on the output of this power supply. Now it's snaking across the screen because it's displaying information, but the information that's displayed is not synchronized with the input signal. So we have on our scope over here on the left-hand knob on this scope, it's got something called trigger. And this is the line we use to actually allow the scope to look at the input waveform and synchronize the scope with the input signal. And notice what happened. It did what? It froze it. Now this goes on and 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 on. I'm going to slow the speed down. This will happen until I do what? I'm going to come over, it's going to happen until I come over and unplug it. And it's gone, right? Plug it back in, there it is. Now what we're going to get out of this is this has nothing to do with RMS because this is not a sine wave, right? You understand that? This is DC. We call it pulsating DC. Why do we call it pulsating DC? Because it's a series of pulses. And of course, we're not going to get, so this right here we call VP. This right here is going to be nothing. So the average would be this averaged with this, right? You understand that? And this average is going to be, this is going to be 0. This is going to be some value. We look at our chart and we see that we calculate the, first of all, I need to find out what V peak is. Here I can measure it, but we should be able to figure this out. So my transformer is rated at 110 volts. That's 110 volts RMS, right? You understand. Then I'm going to run this through a transformer. So now we're dealing with 12.6 volts. So this right here is gone again, right? You understand that? Because the 12.6 volts is what's feeding my circuit. Okay, so what do I need to do now if I want to calculate the average DC? First of all, what's the formula? So you look at the formula sheet, it's got like we're dealing with a half wave, see that? So we're looking for something called, let me find the formula sheet, I'm going to show you all the right equation. So we're looking at unregulated DC power supplies, that's what we're at, unfiltered, and what does it say? I'm sorry, we're looking at AC. So let's look at AC. It says, okay, let's look at the formula first. DC average is equal to what? It's equal to V peak out over pi. I'm looking at equation, I'm looking at equation 14, because this is half average HW. What does HW stand for? Half wave. I understand that. What's the formula? V peak out over pi. Well, this 12.6 volts is not V peak. This is what? RMS. So we look up at our general AC formulas, and what do I need to solve for V peak? Equation 9. So I'd say V peak would be equal to 12.6 divided by what? 0.707. You can also multiply it by 1.414 if you want to. You get the same answer. So what do we got for VP? Are we okay? Everybody okay? Yes or no? At the moment. Okay. What next, guys? Well, yes and no. The problem is, what we did is we just calculated the peak voltage right here. But the output voltage is not set by the what we call V peak in, it's set by what we call V peak out, or V peak secondary. So what I'm going to do is I'm going to take the 17.8 and I'm going to subtract 0.7 from it, because this is a silicon diode, forward biased, right, when it's working. Then that'd come up and give me what? 17.1 volts. DC. Not yet, still DC. That's V peak out. Let me put my equation in. V peak out. So it says V peak out. Y'all see what it says V peak out? V peak out is equal to what? Equation 13. V peak out halfway is equal to V peak out of the secondary minus the VF of the diode. Y'all understand that equation? Huh? Equation 13, what did I tell you? Equation 13. V peak out HW, what does HW stand for? Halfway, is equal to V peak secondary. What's V peak secondary? Right there. Minus VF. What's VF? That's the forward voltage drop of the diode. Go back and look at about the last few lectures. Well, there's three equations there. One of them says full, one of them says center tap, one of them says bridge, one of them says V, one I'm looking at, and y'all got the same one I got. It's got V peak, then it's got out HW. That's the one I'm looking at. Equals the V peak on the secondary, what? Minus VF. What's VF? That's the forward voltage drop of the diode when it's forward biased. This is silicon, so we're using second approximation, so we're going to use 0.7 volts. So 17.8 minus 0.7, if y'all can see that, I know that's a crummy, would be 17.1. Okay. Then we're going to move over to equation 14. What does 14 say? My DC voltage, my voltage DC, is going to be equal to what? V peak out, 17.1 divided by 0.707. So what should we measure? $5.4. So I've got my meter up here. I'm going to turn it on. Got a relay here. I've lost my stand. I need to build me one. Okay. I'm going to take my camera and put it on my meter. And I'm going to put it on DC. Right? And I'm going to take my black lead and put it on my common. I'm going to go across my load. And it's measuring 6.02 volts. Huh? Huh? 600 millivolts off. And what's the difference? Of course, the transformer's rated at 110. It says 6.3 at 110, but we're putting almost 120 volts in the primary. So 6 point, okay. Now this is what it looks like on an oscilloscope. That's what it measures on the meter. So this is the peak right here. Now what we do on a scope, by the way, is we try to make, to measure the voltage, we try to make it big as we possibly can. So right now, the scope is set up to measure AC. I've got my zero reference right here in the center. Well, this is DC. I don't need my zero reference to be set in the center, right? You understand? So what I'm going to do is I'm going to take, we got this control right here called position control, and I'm going to take this and I'm going to move it down. I like to move it down to right there. But notice it shows me my 0 volt reference is moved right here. Okay. Then what I'm going to do is I'm going to take these volt per division and I'm going to make that as big as I possibly can make it. And still keeping it on the screen. So this is the best we can do right there. Okay. So now what I'm going to do, now I'm going to measure this peak voltage. Now we calculated what it was, right? You understand? We expect it to be 17.1 volts. But now we can measure it with my scope. I can't measure it with my meter. My meter is going to give us an average. All right, you understand that? I'm going to take this control right here, which allows me to change the position. You can see what I'm going to do. I'm going to put it right on the line. Now what I'm looking at here, it says channel 1 is set up for 5 volts per division. Now that's 5 volts per major division. So that major division right there, that would be 5 volts. That would be what? 10. That would be 15. Now this is 5 volts per division. So that's right there. So we're getting almost 20 volts peak out. We calculated 17.1, but we're getting 20. And why? Well, the transformers, we don't have 110 volts on the transformer, but using 110 volts, what the transformer's rated at still was what? Was still close enough for us to get what we need. Everybody understand that? And you can go to your house. Are you going to measure 120 volts at your house? No. We depend on where you're at and how far you're away from the transformer, what tap they use. They've only got so many taps on that transformer up there.
Okay, say your power device requires 40 hours.
Well, if
There are certain tolerance.
there's always a tolerance.
I mean, but is there certain one big boom that that's sensitive?
I mean, you wouldn't double the voltage. You have to remember the power. Y'all understand, if I double the voltage to a circuit, what happens to the power delivered to the circuit? This is a really important concept to understand, guys. Huh? If I double the voltage, now we're not talking about the source. You said, now wait a minute, you said power don't change, but that's the source, that's transformer. We're talking about a load. I've got a resistor out there and I'm putting 5 volts on it. And I raise that voltage up to 10 volts, what happens to the power dissipated by the resistor? Well, we got one resistor, so the voltage is going to be the same. I mean, we're not changing the voltage. Somebody give me, so how many people say it's going to double? Come on, Barry. Is it going to? I hope not. If you double the voltage to a circuit, the current's going to go down. Jeez, guys, this is. Yeah, but you're talking about the source. You're talking about the transformer. I'm talking about at the load. I'm not talking about what's going on with me getting power from point A to point B. If I'm in if I step the voltage up in a transformer, it's transferring power. Then, huh? Yeah, but we're talking about the load. We're talking about load out here. The guy that's out here doing the work. We're not talking about the transformers. And that's some people get confused with the transformers, what's going on with the source, and what's going on at the load. So let's say I come over here and I have a resistor. So this is why loads are designed around a certain voltage. Y'all understand that? So that means, okay, if I turn on a 100-watt light bulb at my house, the power plant over here is going to have to give me 100 watts, period. Y'all understand? But what would happen if the voltage at the load went up? Well, now we're not talking about the source. We're talking about, okay, what's going to happen at the load? Not the source, what's going to happen at the load. So here I got, let's just use a DC circuit. Now let's use a 1K resistor. Okay, now let's start off with 10 volts. 10 volts would be equal to 1 milliamp. So P would be equal to I times E. So it'd be 1 milli times 10. What does that give me? Huh? What's that? Okay, it gives me 10 milliwatts. Okay, guys, what will happen if something goes on and for some reason my source doubles? So this goes to 20 volts. My current would go to 20 milliamps. Now, if you say it doubles, then this thing should have went up to 20. This guy right here should have went. So I'm changing the value of the source, right? You understand? So this would be like me taking a light bulb that's rated at 110 volts and putting it in a 240 socket. Now, I'm not changing the source, right? You understand that? What I'm doing is changing the voltage applied to the load. So what would happen? Did the power double? No, it did not double. So power, so if I double this, that would be 20. But when I do the math, it says power would be equal to 20 volts times 20 milliamps. If you can come up with 20 out of that, then you're better than me. So all of a sudden it was 10, now it's what? It quadruples. the power quadruples because V and I are proportional. If you double the voltage to a circuit, the current doubles, and power is equal to V times I. So power varies with the square. If you go down, it's 1 over the square. If you go up, it's the square. So this is why voltage is so dang critical, right? So if you took a light bulb that's rated at 240 volts and you put it in a 120 volt socket, you probably wouldn't even see it glow because it's not getting enough power. My mom called me out to her house one day and says, "Son, my electric stove won't even boil water anymore." And I went out there and the dang thing had 120 volts on it instead of 240. So an 1800 watt element was only doing 1/4 of the power. It wasn't even getting hot enough to boil water. And what happened, she lost one of the legs coming down from her transformer. So the element was seeing 120 volts instead of 240. So it means if power goes, what would happen to the power if I half the voltage? So we started off with 10. If I half it, it would go to 5. And why I'm using 1K? Because 1K is 1 milliamp per volt. Really neat. So now my power would be equal to 5 volts times 5 milli. So did it half? No, it didn't half. We started off with 10, right? So this would be what? 2.5 milliwatts. So it went down by a fourth, right? You understand that? So power varies with the square of the voltage you apply to the load. But people get confused once we start talking about transformers. Transformers are not sending voltage. They're not sending current. They're sending power, but they're going to have to do it at a current level and a voltage level. So this is the difference between the source and what's going on at the load, right? You understand? So loads are designed around a certain voltage. So you couldn't take an air conditioner that's rated at 120 volts and say, well, I'm going to hook this thing up, I'm going to hook it up to 240, it'll get colder in here. As soon as you do it, the air conditioner is going to burn up in a heartbeat, right? You understand? Because that air conditioner is designed around 110 volts, 120 volts. So this is why it's imperative that you put the right voltage on a device. Is that if you put the wrong voltage on there, you're going to have problems with power. So a motor, if you didn't put enough voltage on the motor might not generate enough power to start. And then it would burn up, which is strange. I mean, you say, well, because it's not producing something that it's supposed to be producing when it starts rotating. So yeah, if I went to a different transformer and hooked this up, it might burn up this resistor. But so what we got up here, by the way, is what do we use? This we call this unregulated. What's regulated mean, by the way? So what does regulation mean? It don't mean a law. So right here, this is a regulator. So what would y'all think that would mean? Well, yeah, what it does, it tries to maintain a constant output. So what we end up with is we start off with this, and then we're going to add this filter. So what do we get out of this guy? Well, this guy, we're going to get this. Then we're going to add a filter. And what the filter is going to do is it's going to turn it into sure enough DC. But notice what it's doing across the top. It's doing what? It's got this little ripple across the top, right? We call that unregulated DC. Now look, when we run it through the regulator, what we get out? We get sure enough DC. So a regulator is an electronic circuit that maintains a constant output, tries to maintain. There's no such thing as a perfect regulator. So you can go out there on your car, if your regulator's working okay, you crank it up, go out there and put your voltmeter on there, and then start turning on your lights and turn on your air conditioner. You'll see it maintains about exactly the same voltage because it's regulated, right? If your regulator goes out, I don't know if you've ever seen that before, people turn on their lights and they dim because the regulator's not regulating anymore. So normally what happens is we have opposition down this circuit. If my load pulls more load, then everything down here would try to drop more voltage unless we have a regulator which is going to maintain the output. So when we say unregulated power supplies, that means if you put a load on it, the voltage goes down. If you take the load off, the voltage goes up because of Ohm's law, right? V is equal I times R. So this is what we're working at. So I guarantee you this right here is a regulated power supply.
So it's all coming through your calculator?
No. Well, it's regulated at the generator.
Because, I mean, what made me think of that was their certificate have like.
Well, the problem is that it's regulated at the generator. It's regulated at the source. So Alabama Power outputs a perfect sine wave at the source, but then it's got to go through all these transformers down there. And then, of course, what happens is you have line loss. You have resistance in the wire. So people don't understand that. So your air conditioner kicks on, and then your lights dim a little bit. It's because of line loss. You might be a pretty good deal away from your transformer, right? You understand? A lot of people, they'll be hooked up to a transformer. They have 3 or 4 houses hooked up to the same transformer, and some of those down drops can get pretty long. Or you might even have a loose connection out there. Guys come in and make the connections on the transformer. If you got introduce the resistance in the wire, then it's going to cause you a problem. Or your circuit breaker might be going down. So it might have resistance too, but there's resistance somewhere in the line. And no, they can't regulate. They can't regulate it at your house. You could probably do it. No, it can't do it at the it's just a transformer. How would a transformer can't regulate? A transformer does this. And then the transformer has resistance. In one class we used to teach in transformers, they actually calculated the resistance. So what you do is you short out the secondary, and you have what we call a variac on the input. A variac is a device that you can put a variable AC voltage with. And then what they'd do is they'd crank it up and measure the current, and then they could calculate the resistance of the transformer, the actual true resistance of the transformer. So transformers drop voltage. I mean, it's just that simple. So when they give you 12.6 volts, that 12.6 volts would be at 1 amp. So that's another reason we're getting more voltage out, is that this transformer is rated at 1 amp, and we're not nearly pulling 1 amp out of this. So now my transformers give me a little higher voltage than what I think, right? You understand? For 2 reasons. One reason we're putting 120 volts in it, and the other reason we're not loading correctly. So yeah, they could regulate it with an electronic circuit, but now instead of your power would probably cost you $2,000 or $3,000 a month instead of $100 something bucks. Seems like it is. And that's why we allow this input to vary a lot. So we'll learn this down the path, and we'll learn how we calculate this, how we come up with this, and then what's required here to get this. Now what we want is we want more here than we regulate at. Does that make sense? And if you have more there than you regulate at, then you can let the unregulated can actually vary over a range, and you still get really good output voltage. But that's what we'll learn as we go along. So the regulator is a circuit that maintains a constant DC output. Tries to. You should say there's no such thing as a perfect regulator. To the load with varying input voltages and varying load currents. So that means I can come in and we've got 120 volts here. If I've got a regulated power supply, I get the same voltage out. I go home and it's got 110 volts. I plug that power supply in, I get the same voltage out. So even though the voltage varies on the input, and then I can raise my windows, I can lower my windows in my car, I can turn my radio on, I can crank it up, I can turn it down, and we still pretty much get the same thing out of our alternator because it's regulated. Go out there and don't crank your car and put your voltmeter across your battery and start turning lights and stuff on. You'll see the voltage drop down because it's not what? It's not regulated. Regulators consist of a single electronic device in the form of an integrated circuit or many discrete electronic devices, and we'll look at that too. So you can buy voltage regulators, And we'll look at some of those too. We'll actually tear the trainer apart and let you look in and see the power supplies inside the trainer, which is pretty neat. Okay, unregulated. We're dealing with half wave, consists of AC source. This is the cheapest you got. All you need is an AC source. You probably you could use a diode and you can use load. So you could hook this thing up directly to Alabama Power if that's the DC you need. If you needed a lower DC, then you'd have to go through a what? You'd have to go through a transformer and step it down. If you needed a higher voltage than what's available in Alabama Power, you'd use a step-up transformer. That makes sense. But you don't need it. You don't need it. I mean, you can come right off Alabama Power if you wanted to. If the anode is pointing toward the source, then this is going to give us a positive power supply. If the cathode is pointing toward the source, then we get a negative power supply. So it's real easy to look at. So right here, wherever my power supply is at, this would be a positive power. Here's my source right here. The anode is pointing toward the source. This would be a positive power supply. If I see the cathode pointing toward the source, this is going to be a negative power supply. You don't have to follow current. We could trace current all day long, but that's just a really nice rule of thumb. So I'll come over here and I'll look at my scope. My meter would measure positive. Okay, I'm going to put this back in the center. And then I'm going to change this. I'm not going to unplug it. It's only 12 volts. But y'all don't do this. And I'm going to put it in there that way. Try to anyway, guys. Then I'm going to go in. You got to hit the switch. Oh, I hook up my meter, and now what do I have? I mean, my scope, I have negative DC. All I did was do what? Now I got the cathode turning towards source. We're out of sync. So here's my T. That's what and notice the voltage is never getting up here. So that's what we actually synchronize with, the voltage level. So I'm going to come over here and take the trigger level on my scope. A white line will pop up. And all I have to do is move that white line down inside the signal. And then now the scope is synchronized. And look, it just stopped. See that? Now the scope is synchronized with the signal. There's negative DC. All I did to get negative DC is to do what? Turn the diode around. So now the cathode is pointing toward the source. Y'all understand that? Pretty neat. Now, what are we going to use this for? This is half wave, and why do we call it half wave? Because we're only getting half of the sine wave. We call this half wave. Here's 0 volts up here, by the way, guys. Let's put it online. We should get the same thing negative that we got positive. The math is the same. The only thing you've got to do is understand the sign, right? You understand? Well, calculating the DC average would be the same. I mean, if I come over here and put my meter and I hook it up the same way, so I'm going to put it on the common at the bottom of my resistor. I'm going to put my meter on there, and now it's measuring a negative 6 point. See, now it's negative, right? You understand? Can y'all see that? Now it shows up better, right? I'm going to put my meter across the transformer. What's it going to measure? So I've got my meter right here. It's measured minus here. I'm going to put it across the transformer, and it measures 0. So how could I have a minus 6.1 volt right here and have 0 volts right there? Because I got my meter on it. I got my meter on DC. And this gets people screwed up too. They think they can just take a meter. Now we got 2 voltages in the circuit. We got an AC voltage on one side of the diode. We got a DC voltage on the other side of the diode. So my meter's taking the DC average of a cycle. What's the DC average of a cycle? 0. And that's why we have to use the root mean square, the root of the means of the squares, right? You understand, to get that effective voltage. So RMS gives us the effective voltage where the negatives do not cancel out the positives. Y'all understand that? And that gets people, they'll be in here probing, and they won't put out, and this just gets me too. They'll come over here and measure, they'll record a minus 6 point volts there, and they'll put 0 volts right there, and they don't realize you can't have minus 6 volts over here and no voltage from your source, right? So if I wanted to measure AC, what I need to do is put my meter on AC, right? And so here's this. So we got 14 volts out, you know. I'm gonna come across my hair, and my meter measures something weird. But this is, it thinks this is RMS, by the way, so it's taking 0.707. And usually when I turn it around and hook it up backwards, we get a different reading. This is giving me something. So that gives people problems too. So what it does is, even though it's DC, it's taking the RMS value of that DC, right? You understand? So make sure your meter is on the range that you're checking. AC is pretty easy, because if you put your meter in, if you put your DC meter in an AC circuit, it's going to measure 0. But if you put your DC meter, your AC meter in a DC circuit, it's going to measure something. But it's going to be what? It's going to be wrong. Y'all understand that? What do we do with half-wave rectifiers? Well, we use them for all kinds of things. What I've got up here is I've got a little motor. Motors don't care. They love DC. It can be, oh, I got my camera up there. So here's my little motor right here. I'm going to come up here. I got a piece of tape on it. I don't know if y'all can see it spinning or not. I probably need to put a piece of masking tape on it. I don't put it across my little DC power supply. Works great. You know, DC motors don't care if it's pulsating DC. Electronics wouldn't like it, but DC don't care. So we do this a lot to run motors. All we need to do is make sure we get the right voltage out to run the motor. What would happen if I put my motor across AC? Well, it's not going to run. It's going to sit there and try to vibrate back and forth. You'll see it. Can you hear it? It's a DC motor. It's not going to run on AC. It tries to. By the way, we got a motor called a universal motor. Guess what a universal motor will do? It'll run on AC or DC. It's a series motor for some reasons we're not going to talk about. But look here, that's like running real nice. Make sure I have a 1 amp transformer plenty to run this motor. Got a 1 amp diode plenty to run the motor. If I put the little silver, the little 914 that we passed around the other day, it'd probably burn it up. Now the motor's running in one direction, and if I reverse the diode, the motor's going to run the other direction. So DC motors are real easy to control. You just control the polarity of the voltage is going to do it. So how we doing? Okay, I'll take another break. I beat you on that one, Larry.